Hello, everyone. Welcome back. I hope you had time to catch your lunch and you're excited for the next round of talks that we have lined up for you. We'll keep them interesting and exciting so that you don't fall asleep. Up next, we have with us Govil Khatri. Govil is working on OPUS, which is an online machine learning platform that provides end to end ML solutions to manage data, run model predictions, do the deployments, and monitoring at scale. Joining with him for this session today, we have Sarthak Agarwal. Sarthak is a software developer in the M3 team of Flipkart that handles merchandising, monetization, and marketing. For the past couple of years, he's been working along with Govil on this platform. Let's take a deep dive into Opus, an online machine learning platform that has helped the business by improving user engagement and conversions. Over to you, Govil.
Uh, Thank you so much, Sarika. Can you guys hear me? Just quick show of hands, please. Okay, cool. Hi guys, good afternoon. My name is Govil. So, me and my colleague Sarthak are here to present OPUS, which is about user response modeling, solving user response modeling use cases via online learning. So in this talk, basically, we are going to take you through a journey where what are the possible online user response modeling use cases which are there in Flipkart, and how we are trying to solve them, and what has been our journey in terms of multiple approaches that we have tried. So let's get on with it. So let's let me take you through what is basically user response modeling. So as the name suggests, user response modeling is basically trying to understand users' behavior on a platform, which is Flipkart. Now, if you can imagine what a user action, what are the possible user actions which can be there on Flipkart, which is it could be a click on a content or on a product, it could be a purchase of a product, or it could be add to cart, it could be add to wish list, and etc. and etc. So, in a very simple words, what we're trying to do here is we're trying to predict users' actions on various real estates of Flipkart. So let's go deep dive into this. So what you see here is the Flipkart homepage, where what we do is when a user comes to Flipkart homepage, we need to respond to the content, let's say merchandising content or recommendations content or advertisement contents, which are towards users liking as well as his or his her affinities. Now, the what do we so what is the user response modeling use case here? So what do we do is we basically predict or we predict the action of a user in terms of a click or a purchase. So let's say if we show this content to this user, will the user actually go and click on this content, or user may end up buying the related products to the content? So these are one of the group of use cases that are available on Flipkart. So let's try to understand more use cases here. So Flipkart sends communications to all the users. So when I say communication, it can be a push notification on the mobile app, it can be a mobile device, or it can be an email, it can be an SMS, or it can be an in-app notification. So what happens here is Flipkart, before sending out a communication, we have a certain content pool. We have certain pool of communications which are eligible to be sent to this user at this point in time. Now, what we are trying to predict here in the form of a user response modeling use cases, we try to see that if we send this communication to user, will the user open it, or it may lead to a purchase from that communication. So this is one of the other use cases. Now, in the same lines, let's consider one more use cases here. One more use case here, which is, let's say if I send this communication to the user, will user get annoyed, or user in the form of action, user can actually go to Flipkart app and unsubscribe all the communications from Flipkart. So you see, these are very important use cases for Flipkart business and Flipkart users as a whole, which we're trying to solve in Flipkart. So now we know the gist of what are the use cases we are trying to solve here. Let's try to understand what are the approaches that we have taken to solve these use cases. So a couple of years back, we tried one of the traditional approach, which is batch learning, where we generated a big training data set. Now, data scientists and engineers would train their models on that training data set, and they will generate a model. Now, model will go online and it will serve the actual users. Now, for example, the training data set that we're talking here, given a homepage scenario, let's say, will belong from at least 1 week to at least 6 months of data. Now, of course, we went live and we saw multiple challenges with this approach. And one of the few challenges you can also guess actually. So I've summarized a few of the challenges for you. Let's take this up one by one. So one of the major challenge that we saw with this traditional approach is basically we were unable to understand user behavior or trends or patterns or shopping patterns on flipkart.com quickly because of the whole process of generating large data and training a model on that large data and then releasing a model and productionizing that model. Was The whole process was too slow, right? Because of the process which was too slow, there was a huge gap between actual user feedback and the whole serving, and an ecosystem like Flipkart, where entities like offers, discounts, or contents on homepage or recommendations, very short-lived nature, or events like flash sales or sales of any 3 to 4 days of period. Generally, they are short-lived, and if our process is too long, we'll never be able to cope up with, or we'll never be able to learn all those quick trends on within the model. So that is one of the challenges that we saw with this approach. Other approach was, so our data scientists and engineers, let's say, they will of course try to do multiple experiments and exploratory analysis on these models and data, where they would try to tweak multiple features or some hypertuning parameters or certain other configurations. Now, our system, where we were training on a large training data set, any model or any experiment to do usually takes equal amount of time to productionize a model. So doing exploratory analysis or experimentation was also very linearly expensive in that scenario. So this was one of the challenges that we saw. So other challenges that we saw, and I think everyone is aware of, is parity issues, where the feature sourcing in online world or feature sourcing in offline world while generating the training data is generally different. And because of that, there are a lot of parity issues between online and offline world. And whatever goodness that we are seeing in an offline world is generally not seen in online world. And that's where it is important that we actually, so what we did after that, we basically went back to whiteboard, paper, pen, and we wanted to revise like what we really want to solve and how our new platform should look like, what are the new solutions should look like. So these are the new expectations that we jotted down at that point in time. So one of the major expectation was we should be able to learn user intent or user shopping patterns or behaviors on our platform quickly. That we have already discussed this. Now, another expectation that we had is in a Flipkart-like platform where all across Flipkart, multiple data scientists are trying to solve multiple user response modeling use cases, and we needed some kind of self-serving or some kind of ownership model for their training modules, right? So data scientists should be able to configure their models, should be able to do experimental analysis or exploratory analysis on their models and trainers with a click of a button. So this was another important expectation which we had, which relates to the configurability of the training module. So other expectation that we had in this scenario is actually scale. So if you understand Flipkart, there is wherever there is a constantly where our user base is increasing, our scale of every content on homepage or communications or any other use case response models across Flipkart, the scale is always increasing. And so whatever solution that we need to build or we are about to build should always keep up with the Flipkart scale. Now, let me add one more point here. So when we say, so in this scenario of your user response modeling, where these ranking models, the amount of ranking candidates that we need to score within a particular request, let's say, it could go to more than 10,000. For example, on a home page, if we have to show 100 contents, which are the best shortlisted 100 contents for that user's liking or interests, we might need to score at least 10,000 contents in that within that user's request. unlike a classification problem where the amount of ranking candidates could just be one, right? But for example, whether this order is a fraud order or not. So whatever we wanted to build should always keep up with the Flipkart scale. And of course, monitor and visualizing performance of models and features and experiments in our dashboards. So so, so that's where Opus comes into picture. So, if I have to define, Opus is basically an ML platform in Flipkart, basically catering to all user response modeling use cases via online learning. Now, I coined this word at the start also, online learning. So, what is actually an online learning? Let's try to understand this in depth. So, online learning, or shall I call it incremental learning, is basically another form of machine learning where we generate the batches in a sequential order. Now, the batches, whenever the batches are generated, a single batch will be used to train an online predictor. And once an online predictor change reads or train itself from that batch, it updates all of its feature weights accordingly. Now, let's see this example here. So 1 p.m., let's say 1 p.m. is one batch of data, which holds the data from 1 p.m. to 1:59 p.m. Now, once this batch is available, the Model 1 predictor will be trained on this batch, and Model 1 will adjust its weights accordingly. Now, Model 1 can go into an online world and serve all the live users till the time another batch is available. Now, once the other batch is available, the same model state can be used to train on the 2 p.m. batch. And similarly, the Model 2 can go online and serve the live users. Now, you see, this loop is basically endless. So what we are doing here is the model basically stores the learning from a very long time. It stores the patterns and the feature weights, and it basically depends upon us how fast a model can be. Now, of course, when I demonstrated this example, 1 p.m., 2 p.m., now this can be configured now depending upon the data availability in any of the platform. So in our cases, if we can configure it to, let's say, a few minutes or few 30 minutes or 15 minutes batch or even 1 hour in few of the scenarios. So that's where online learning help us in keeping up the user intent or user behavior, learning on top of them in a very faster pace. Now, also, now let's say the other example that we, if you remember, challenge that if you remember, we had was data scientists should be able to train their models or experiment with their models, in configurable, and they should be so. For example, model one can be forked out, and the model one can be configured in terms of multiple different features or different hypertuning parameters. And once the model one dash is available, it can continue to train with Model 1 on the same batch of data. We are going to talk about this in the coming slides in detail, how we have tried to solve this. But let's try to understand now how Opus platform is built. I'll try to give you a 10,000 feet view of how the architecture of the whole Opus platform looks like. So any ML platform at least has three steps. One of the steps that you see is training data generation. So you generate the training data. Other thing is you train on that training data, and third thing is you productionize the model. So what are we doing differently here? Let me focus on those parts. So let's start with the first step, which is training data generation. So if you remember, I talked about parity issues in our traditional approaches. So what we did is basically in our batch, while generating a batch for training, our source of data is actually the serving logs, which means whenever clients do the inferencing of any ranking candidate, they log all the features used as is in their serving logs. And our jobs, training data generation modules, depends upon that log as the right source of data for those features. And of course, labels are available in a separate tables. Now, once this features which are used in the online world are available with the labels, we just combine these two and generate the training data. So if you see, there is no other feature sourcing here. Basically, our dependence on serving logs has helped us in reducing parity issues to nearly zero. And we can always, relate our performance in the offline world to the online world. Now, let's say the training batches are generated sequentially. Now, what we do in the training is our data scientists and engineers can configure multiple models, multiple variations of the models in terms of features, and as I discussed, hypertuning parameters. Now, all those models will be trained parallelly, given on the same batch. So once all those models are trained, what you will see is multiple models which are generated after the training module. Now, of course, only one or few of them can go and serve the online world. Let's say only there could be only one model which is productionized for the real life use, real time scenarios, or there could be two models for, let's say, AB scenarios. Now, what our data scientists and engineers can do here is they can define a winner configuration in terms of the offline metrics. So let's say a model which has the highest metrics of AUC and RIG, let's say, will be considered as a winner model. Now, once our winner model module sees and reads all the offline metrics of the generated models in that batch, it decides the winner and publishes that to model repository. Now, once the model are uploaded and published to the model repository, the serving teams can quickly, refresh from a model repository and start serving the online users. And again, they start logging the serving logs, and the whole loop basically continues as is. So now I would like to invite my colleague Sarthak here to, which will take us through how we are actually trying to solve the training part, how data scientists can actually configure multiple type of models, and how they basically can, how are parallelizing the multiple model trainings, and how we're actually, using the Keymaker, which is our inferencing library, and how it seamlessly integrates with the client. Over to you, Sarthak.
Okay. So thank you, Govil. Good afternoon, everyone. So Govil just gave you a bird's eye view of OPUS architecture and how our ML pipeline looks like. So let's deep dive into some key components of our architecture and actually understand how we have built those components. So let's talk about model training first. So let's assume our data generation pipelines have created our early batch of training data. Now, what we want to do is we want to train on that data and generate ML models. So, data scientists are configuring different models, also called grid points, with different feature sets and different hyperparameters. And what we want to do is we want to update the state of these grid points by using this new data batch that we've got. So basically what we do, we take this data batch, we pass them through our trainers, which eventually generates a model. Those models are then pushed to a model repository from where clients can consume those models and then personalize the content that they want to serve. Right? Now, let's take a step back and understand what actually a grid point is. So consider the scenario where we have a production model and it has a certain feature set and some hyperparameters. Now, a data scientist comes and he wants to try something new. He introduces an experimental model with a different feature set or some different hyperparameters. Now, in our entire training setup, we consider each model to be a grid point. So, grid points are very simply just a different variation of a similar model that trained on the same data. Each grid point differ only in its feature set as well as its hyperparameters. And what this enabled us to do was we were very easily able to group and train different variations of the same model together. Right? So now at Flipkart, we are
I'm
dealing
sorry,
with
Sarthak, to break you. Your voice is breaking a lot. Can you not use the earpods?
okay, one second. Is this fine now?
Yeah, it's much clear.
Okay.
Thank you.
So, yeah, so at Flipkart, we are dealing with a lot of data and are solving multiple use cases on a daily basis. So, uh, this means that the number of models that we want to train are increasing day by day. So, we wanted our training system to scale alongside. We wanted to train multiple models concurrently, and that is what we did. By loading our training data only once, we are able to train multiple grid points on it concurrently, and moreover our trainers are stateless in nature, so this allowed us to horizontally scale our system. Whenever we want to train more models, we can just add more machines and we are good to go. So this was our training pipeline. This was our training step basically. Now we have trained our models, but how do we use them actually? Like how the client systems, how do they actually use those models and rank content? Let's have a look at that. To understand this, let's consider a very simple problem statement. A Flipkart user comes to logs into flipkart.com, or maybe uses the Flipkart app, and we want to basically rank and serve personalized content for him on Flipkart homepage at Flipkart scale. So at a very high level, what happens is the request hits the Flipkart servers, and the homepage service basically has a huge content pool of millions of contents, basically having different widgets, different advertisements. So we basically want to understand what's the best content for every user. So to understand that, we basically want to get some sort of a score for every content, which tells us the probability of a user clicking on it or engaging with it, right? Now, once we have that score, we can use those scores to rank and filter content and then showcase them to the user. But to actually calculate those scores, we need some sort of an intelligent module that can help us score this content, right? And then help us rank and filter it. And this is where Keymaker comes in. Keymaker is an in-memory scoring library that integrates seamlessly with client systems, and it helps in scoring content by leveraging the intelligence that was provided by the model. So it's basically the brain in this entire setup, and it's helping us understand what's the best content for the user. So what exactly happens in Keymaker? So whatever models we trained, we push them to model repository. Keymaker gets them from model repository, parses them, and from the model it parses and gets the feature to feature weight mappings and stores them in some specialized data structures that we call storage engines. Next, what happens is whenever we want to score a piece of content, we get its raw features. Now, those raw features could be something like the title of a widget, or maybe the average selling price of that widget, or it could be some user level features like what's the gender of the user, or whether the user is married or not. So all sorts of those things. Now we take those raw features and we convert them to Opus model features using a very rich feature repository. Once we have all the features, we need to get the corresponding feature weights for those, right? So our model scorer interacts with the storage engine, and for every feature it gets all the feature weights, it aggregates them, and then for that particular content it generates a score, and that score is then eventually used to rank the content. Now I have mentioned about these storage engines, but what are they exactly and how are they helping us? So, storage engines are very simply a set of basic data structures that are built specifically to cater to different use cases of ours, with involving different kinds of feature sets. So, according to the feature set that a model is using, we can use different storage engines for that. Now, if you have a very basic use case where you just want a simple mapping between feature to feature weight, then you can use a simple map storage engine for that. But you have some use case where you want to optimize for multiple cross features, then we have a different storage engine for that as well. And if you have a particular feature set where the feature distribution is very sparse in nature, then we have a storage engine for that as well. So, how are these storage engines helping us? Using them, we are able to retrieve our feature weights very quickly. And faster retrieval of all these weights help us massively in reducing the overall time taken to score contents. Also, since Keymaker is an in-memory library that sits inside the client system, we also support storing these feature weights on top of heap memory, or we can store them off the heap memory as well to reduce GC pressure on client systems. Now, all of these efforts combined have helped Keymaker rank content at extremely low latencies, and that is what we wanted at the end of the day, right? So, we have talked about how we are training our models and how client systems can use those models. One other key aspect of our platform, which actually makes it a platform in the truest sense of the word, is the configurability it provides. So in a very in the life of a data scientist, a very normal day involves addition and removal of features, playing around with different hyperparameters, adding new models, or experimenting with different algorithms, right? Now we wanted to streamline this entire process for them. We work towards making our system self-serve. And how did it help us? So now data scientists are able to easily and quickly run multiple experiments for different models and features. Since we are able to run multiple experiments quickly, we are able to launch different models and different features into production even quicker, right? On top of that, we were also able to solve for some very specific use cases. So let's consider the scenario of Flipkart sales. So if we take a user, an average user, he might have a certain set of preferences or affinities during normal days, but whenever a sale starts, his behavior might completely change, and we want to actually capture that behavior differently. So we started using specialized models during those sale durations. So since our system is very configurable with very minimal changes, we are able to seamlessly switch the model that we are using in production. So when we are running in normal days, we have a normal model going on, and then whenever sale starts, we quickly change the model. We start using the sale model, and whenever sale ends, we very easily revert it back as well. So these are some of the benefits that we are getting by making our system configurable, right? Now we have trained a model and we have ranked also using the model. But how do we know how well we are ranking? We need some way to monitor the performance of the model. And for that, Opus offers different metrics. Uh, Opus offers some data level metrics which help us understand the feature distribution in our training data set. It offers some model level metrics like AUC and RAG, which help us understand how the model is actually performing. Using metrics like RMSE, MDAPE, and MAPE, we are able to understand whether the model is actually performing as expected in production or not, and if there is any disparity that is there between production and the offline setup where we test our models, right? Additionally, we also have some feature level metrics that help us understand how a particular feature is performing and what will be the impact of adding a new feature. So all of these metrics are whenever a client onboards, all of these metrics are provided in easy to use dashboards which help the client visualize all the metrics very easily. So we have talked about a bunch of things like training and ranking and all sorts of those things, but what have we actually managed to achieve till now? So let's see what Opus has actually brought to the table so far. So with an ever increasing user base of Flipkart and with more traffic than ever on Flipkart has a lot of raw data, and Opus data pipelines are processing all of those raw data. Close to around 100 TBs worth of data we are processing on a daily basis, and we are generating close to around 1 billion training data points. On those training data points, we are training close to around 100 models on an hourly basis, which roughly translates to around 2000 models daily. And using those models, we are able to rank a huge candidate pool at extremely low latencies. So there are systems that rank more than 10,000 contents in under sub 100 in under 100 ms latencies, and that we feel is pretty fast. Also, the effort and time taken to take a model or a new feature from its experimentation phase to production has significantly reduced. So previously, what used to take an ad hoc effort of 4 to 5 days has now reduced to maybe a couple of hours. Also, using our dashboards, we have a greater visibility into how our models are performing, and we are also able to take quick corrective action if they are not performing up to the mark. So this is what Opus has done so far. But what's next in our journey? So, our vision was to make our entire system self serve. And we have managed to do that with our training setup. But self servability of data generation pipelines is something that is yet to be done. So, that's one. Other than that, we have ready to go support for multiple online learning algorithms, but we also want to try out different deep learning models in the online framework as well. So this is what lies ahead of us, and we are very excited for it. So with that, I would like to thank you all for listening to us. We'll open the floor for any questions now. Thank you.